So today we're going to finish up chapter 3, and then we're going to ease our way into chapter 4, just a few slides. So a few things we need to cover in chapter 3. Actually, this will help you do one of your homework questions. I know there's a question about heating and cooling degree days, and I like this concept. I'm not so sure about the 65 degree Fahrenheit sort of thing, but basically what the heating and cooling degree day concept does is you set your thermometer, your thermostat in your house on a particular temperature. And then they use climate data to see how far away, they use climate data to see how far away the temperature outside is from what you're going to set your thermostat. And they do a little difference. And then basically they add all of those differences together throughout the year if it's an annual sort of thing. So, in other words, up here, not so surprising, in Alaska, with regard to turning on their heater, they have 10,470 heating degree days. Okay, I know it seems like how many that can't be. There's only 365 days in a year, but it's for each day. How many degrees away from 65 degrees is it? Okay. So we can pick on Miami, 149 degrees throughout the year that are below 65. Okay. So does that work for you? Then here, heating degree days is the next column. So it's a similar thing, and again, how many of us set our thermostats at 65? I don't know. But in this case, if it's warmer than 65, okay, bless you. Basically, they add up the difference to 65, okay, and then they sum those throughout the year. So here, Florida, if we find Florida, okay, they've got 4,361 cooling degree days. Makes sense. So I was going to show you this, or I will show you this. Few things. This works. So all of these columns, I know they might kind of make you dizzy. They make me dizzy, but for each of the classes I teach, I have the Twitter feed thingy. I like these feeds because actually I post what questions are due, and then I'm like, oh, well, I did say those questions were due. So you guys are this one right here. Your guys, the blue skies. Okay. This is my 9th class. Okay, and actually you guys are dueling. If you open up the course homepage in eCompanion online, you'll see both of these. But I posted something, it's called a handy dandy website for calculating heating and cooling degree days. So it's pretty cool. All we do is we put in our zip code, 52632. Okay. It recognizes us as Keokuk. And there's different tabs. So this is degree day comparison, average daily temperature, cooling degree days, etc. But I thought this is kind of cool. If we go, let's go 2011 to 2015, run report. Okay, so I'm not sure I entirely understand everything, but these are a couple of years. HDD stands for heating degree day, CDD, cooling degree day, and total degree days are adding those both up. So that's kind of neat. This would be annually. I also thought it's cool if you do the tabs across the top there, it actually does some other interesting things. So this is going, each year is a color and kind of showing you what our average daily temperature was. So I think that's kind of neat. So there's that. I'm going to go back to the Twitter feed. The other thing, shout out to Miss Mabin. So if you guys ask a question in class and I don't know the answer, this is also at my Twitter feed where I can look it up and post something. So we were talking about, different devices to measure things. But what if you have a temperature that actually would melt glass? You have a temperature that would melt metal. It's like, how the heck do we do that? And it's kind of an indirect measurement. The website I found, if you read it, to me, it's kind of like that little IR, that little gun that I brought the other day, okay? That's the sort of thing that you would use. Yeah, that was pretty cool. No pun intended. But the other thing that I thought, how do you measure temperature? It kind of goes back to, remember the curve of the sun is like this, right? Remember that curve? And the sun of the earth, the curve of the earth is like this, okay? Big. And remember, like, the sun is clear over here, and the short wavelengths, actually, that's going to be kind of a review sort of thing for you. And the thing over here, the earth is long wavelengths, and it's squatty, okay? So the deal is if you were wanting to know the temperature of something, actually, you could get kind of a profile of the radiation it was sending. Go ahead and slap it on a curve like that, and you could knock out what the temperature is, too. So, but yeah, you definitely could not, and that's an indirect method, too. So that's a good question. Okay. So the other things we need to finish up, before I leave this, let's go to, that's not you guys, it's not us. All right, so we're going to talk about feels like temperatures, and before we go there, let's look at what the feels like temperature is. This is the Weather Channel. No, this is AccuWeather. So right now, our thermometers are reading 28, but the feels like temperature is colder than that, 41, because of the wind. Okay, it's a wind chill effect. That's the next thing we're going to talk about. If this was summertime, okay, our feels like temperature would be because of the humidity. Okay, so we have two feels like temperatures, one in the winter, one in the summer, and they're due to different things. The one in the winter is due to wind, the one in the summer is due to humidity. So let's just jot this down. Let's jot down our 28 degrees. T is equal to 28 degrees Fahrenheit, I assume. Now, do you guys see the wind? I don't yet. I need the wind speed. If I click this. Okay, so they've got us the wind as 0. Well, how did they get 28?
Why is the feels like temperature higher?
Oh, okay. No, check this out. I'm going to do RH, percent relative humidity, is equal to 68%. Isn't that weird? I'm going to put wind is equal to calm. Right? All right, let's go.
Why is it higher?
It's got to be they're factoring in they're doing the other one. Just be patient. We'll come back to this. This is a good learning experience. Okay. So in the wintertime we factor in the wind, and in the summertime we factor in the relative humidity. Okay. So that's why I'm thinking they are factoring. Oh, I should have written the feels like temperature. They said 41. These are all Fahrenheit. Okay. All right.
Why is it again that it feels like 41?
Yeah, we're going to get to that in just a
Oh, we're
minute.
going to get to it, okay.
Yeah. Yeah. It's either that or, I'm trying to think of the Celsius or the, I'll get back to it. We'll come back around to it. I really don't know. So when I talk about these feels like temperatures, actually the feels like, whether it's a wind chill or a heat index, it only affects warm-blooded animals. So your lizards would be fine. Warm-blooded animals count on actually, they are chilled if there's a wind, and warm-blooded animals are oppressed if there's high humidity. Okay, your radiator does not care about the wind or the humidity, like your car. So this is the way it's supposed to work. For instance, if you have a feels like temperature across the top there, if we had a feels like temperature, and this is in degrees Fahrenheit, of, let's say 25, and let's say the wind wasn't calm, but the wind was blowing at 20, okay, then our feels like temperature would be where they intersect. Okay, so the feels like temperature would be 11. If it's, again, still 25, but we have winds that are sustained at 50 miles per hour, youch. Okay, notice then our feels like temperature would be 4. That's kind of how you do that. The purple is very dangerous, blue is bad, and this is also bad. But okay, let's get to the other one. And then we'll revisit that website, I think. Okay, in the summertime, you guys know if it's humid outside, you feel terrible. And this is actually why. There's the heat index temperature will be your feels like temperature. We're going to talk more about this in Unit 2, but if there's already a lot of, if it's really, we're going to talk about humidity in Unit 2. High humidity means there's lots of water vapor. If there's already lots of water vapor, then basically the liquid water does not want to evaporate. And in order for us to cool down, warm-blooded animals to cool down, we count on water evaporating. Okay, water evaporating has a cooling effect. So if water doesn't evaporate because it's too humid, then we feel hot. So there's another table right here. I doubt if this goes down to.
Does that apply to like sweat?
Does it apply to sweat? If sweat is your humidity, I think sweat's not factored into it because that's kind of an individual thing. But sweat.
I mean, like when sweat evaporates, isn't that what cools you off?
Right.
So if it doesn't evaporate.
Right. That's what this slide said. Yeah, if it doesn't evaporate, then you don't get cooled off. Yep. Yep. You got it. Counting on this. So I would do this, but we don't have 28 on here to see if it's a 41. But if the temperature, if your thermometer said 84, and if you were at 60% relative humidity where they intersect, it would feel like, instead of 84, it would feel like 88. If your thermometer said 92, and again the relative humidity was 60, notice that instead of 92, it would feel like 105, which is not good. So that's the feels like temperature. Okay. Bless you. That was AccuWeather. Let's go to Weather Underground.
Absorb.
Coming up. While that's coming up,
Protected. Yep.
weatherunderground.com.
Remember that. I think it's
Where did mine go?
Oh.
Flyer.
I have one picture.
So this is your review sheet.
Good job.
And I think I have these, or I will have these also posted under Doc Sharon. You can use them.
Oh, very cool.
And I'm gonna do, when we do a review session on Monday, this is what we'll go over. I'm sitting here looking at it.
This is me, and I'm like,
I was just gonna let you.
okay, so we have these just next Thursday, and then I have to leave on Friday.
You should try to get this one through her.
Yeah, I know.
I do that.
I suppose. That
And then
one
I
I
have
believe
two
is more
history ones
than
and
the
Friday.
other one. I think that other one, I just think was wrong.
I did too.
Pretty excited about that.
Yeah.
What did you say?
I think that other site was wrong. So doesn't that make more sense to you?
Yeah.
I mean, that makes a lot more sense.
Oh.
I just kind of randomly pulled one up, thought, well, it'll be right. That one was wrong.
That's what I have on my phone, the AccuWeather that I have on my phone, so like, I could be looking at it wrong.
don't
I have that
know.
one on my
Let's
phone.
go back to this and let's refresh it. That is so weird. The real feel.
Yeah, I have that on my phone too.
It says 41 for the real feel on your phone?
How do you?
I have no idea.
A lot.
So should we do a tiebreaker? Let's see. Weather.com is the weather channel.
I can't go.
Tiebreaker. And it's really hard to calculate a wind chill temperature when there's no wind. 2 miles per hour is really slight. We could do a different location, so where is there wind? Let's do,
I don't shower. Unless I get from Jerusalem.
it's not letting me, come on, really? All of these ads, oh my gosh.
Your mouse is having a freak attack.
What's that?
Your mouse is going like
It's having a
freaking
freak
out.
attack. It's having a seizure.
Yeah, it's having spasm or something.
Okay, so well, we need someplace with wind. Anchorage.
I should trust my phone
Coastal
to
Anchorage.
What?
because it says feels like 41, but it's 28.
How do you spell, is it
CH.
Thank you.
I like your glasses.
Is it that how you spell it? I thought so too.
Actually just left it fresh in your house.
I just want someplace with wind. That's not much wind. What? Is it like nighttime there? Okay,
It wouldn't be nighttime, what?
yeah.
It would be early morning. These would be 3 time zones, right?
Well,
Anchorage is-
this one, see the wind is, do you see the wind? Yeah, so it's 5 miles per hour. So if we go back to, you could find at least this one, 5 miles per hour. Oops, wrong one. So 5 miles per hour, just barely on there.
So I'm just trying to check out.
Current temperature. Wait.
How do you know which one?
The ones I'm more sure of.
I don't know. So that would be right up. Uh, 5 miles per hour, and it's about 25 or so. See if I ever do anything impromptu. So they're saying it feels like temperature of 24. So I guess I buy that.
What's the temperature in Keokuk right now? Is it 28?
Yeah, something like that. Depends on which site you look at. What's the temperature in Keokuk?
28.
All right. All right. The sheet I just gave you, it's a review sheet. This is actually what we're going to go through, like I said, on Monday. And I'll record the session. I'll go ahead and post it on Twitter as a video. And then I'll also make something called review pages. This is my review sheet. My review pages are kind of like, basically I take one chapter at a time and I annotate it. So that will also be available under Twitter. So if you're not a Twitterer, you might want to consider that.
Does it cost some money or is it free?
Twitter's free, yep. And if you don't want to do the whole Twitter thing, just open up the website. Like if you guys were going to go check on your grades, you probably click on that online tab, go find this class, okay? Check on your grades. The same place you check on your grades, that sheet that opens up will have the Twitter feed. So, same diff. Yep. Okay, so let's do a few slides in this. Actually, these first few slides in Unit 2 are very similar to stuff that we've covered, so it's kind of nice. It's like deja vu slides.
So you have like a sentence and then you have like a little
I was at
asterisk.
hike the other day
Yeah.
and I was smelling brown stuff, so I was filled with an red and it squirted right up my nose.
It's like explaining something.
Yeah, I had, yeah, it happened.
I'm not a dictionary.
Okay, so this morning, on the way to work, like about 8:15, 8:20, I could see the sun, the disk of the sun getting higher in the sky, and kind of over here, I saw kind of like a little rainbow thingy, and actually that was a very faint sundog.
Did you take a picture?
I did not take a picture, I was driving.
You can still take a picture while driving, it's just not safe.
No, you cannot. Okay, so the thing about we'll be talking more about sundogs, but anytime you see something kind of like colorful that's usually not there, it's probably being caused by the presence of either liquid water particles or ice crystals. And sundogs fall under the latter. So sundogs are because of ice crystals are there. I could actually see kind of a wispy little cloud there, yeah. That's very pretty. This actually, I'm going to dim the lights. Have you ever seen rain? Does that, you guys recognize this?
Yeah.
This is actually, if we're here, it's not raining. If we're over there, it's raining. Okay, you can actually see the cloud letting loose of its liquid water. What clouds are, I'm hoping we're all kind of on the same track with this. Clouds are liquid water droplets. Water vapor, you cannot see. Liquid water, you can see. Okay, so I think that's pretty cool. Now this almost looks like maybe, well, it looks like it's hitting the ground, but have you ever seen it like rain and it didn't hit the ground before? There's a name for that, starts with the letter V, it's called virga. So it just kind of, basically a cloud lets loose of its liquid water and the air is so dry that the liquid water evaporates before it gets to the ground.
Can snow do that too?
Snow can do that too, yeah. Yep, very good.
Is it called the same thing?
I think it's called something else. I don't know. Another good question. But I know virga, and maybe it's called the same thing. So a lot of this stuff, especially early on, these first 10 slides, that's about how far I want to get through if you're kind of a slide counter. These first few slides are like, yeah, we talked about that. And we're going to actually talk about it now more in Unit 2. The hydrological cycle is the water cycle, okay? And when it says atmospheric sources, it's like, well, how do you get ways to get water into the atmosphere, atmospheric source? And so the most obvious way is evaporation. Okay, transpiration is basically from plants. Basically, plants go ahead and get liquid water into its vapor state. And then geospheric sources is how do you get it back to the geosphere. We talked about the atmosphere, the geosphere, the biosphere, and the hydrosphere. So how do you get it back to the earth? Well, rain, precipitation, snow, okay? Then there are a couple of other things you're going to see on the slide, kind of where else is the water? Well, if we have liquid water on the ground, we call that infiltration. Liquid water just on the ground, we call that runoff. If we had liquid water under the Earth's surface, we call that infiltration. That makes more sense, groundwater infiltration. So this slide covers them all. We have precipitation. The clouds basically are liquid water. We're going to call, for when a gas goes to a liquid, that's condensation. So condensation forms the clouds. And then the condensed water will precipitate, either as liquid rain or snow. So this might seem like a deja vu thing, because we talked about that all matter has motion, and I know we talked about absolute zero is basically the temperature at which motion stops, right? So all matter has motion. And kind of related to that, we're going to hone in specifically, again, just to water molecules, okay, because this chapter is about water. So focusing on a water molecule, of course, the formula is H2O. We have the white things are the two hydrogen atoms. The red thing there is the oxygen atom. All molecules kind of have a different properties or tendencies. A water molecule is amazing because actually where the oxygen is, that is what we call partially negative. So you see this little negative right here, where the oxygen is, where the hydrogen, now these are individual molecules, where the hydrogen atoms are, those are partially positive. And it's kind of like a magnet. If you take a north pole and a south pole, okay, if you take something that's negative like oxygen and something that's positive like a hydrogen from another water molecule, okay, they stick together. So those dot there, this actually is what we call an intermolecular bond, or a bond, bonding those two water molecules. Now, matter has all sorts of intermolecular bonds. Like there's intermolecular bonds in this, there's intermolecular bonds in plastic, okay? But these intermolecular bonds are called hydrogen bonds. Not all intermolecular bonds are hydrogen bonds. It's a special kind of strong sort of thing. So kind of from left to right, on the left here we have water in its solid state. You guys probably would tell me if water in its solid state, basically it doesn't move as much, it has less kinetic energy. I think we talked about that, just kind of wiggles. And the other thing is it's really networked together, a lot of these bonds. Okay, so that's water in its solid state, that's ice. If we add heat, it's going to melt, go from solid to a liquid. If we add heat, literally what we're doing is kind of breaking an assortment of those chemical, or not chemical bonds, assortment of those hydrogen bonds. So we have solid ice and we have liquid water. Now, what I would complain about with this, not complain too much, but I wish over here in its liquid state, I wish that they would show some of these intermolecular bonds, because that is the real deal. When water is a liquid, it has some intermolecular bonds. When water's a gas, no intermolecular bonds. Okay. Did we see this video last time? Okay. This should work. It worked last night.
Mm-hmm.
I need to save a little bit of time because we're going to go back and look at your homework right quick. That's due on Monday. One more time. Well, while that's coming up, because I think it will, let's go on to the next slide. I'm going to put this whole slide up here because it's another deja vu slide. So I'll go ahead and draw.
Matter changes. Molecules are in constant motion.
You are evil.
Heat increases.
All right. Okay, so one of the things we need to talk about in Unit 2 again is this idea of phase changing, okay? So you guys would tell me if I'm going to take an ice cube and I want to melt it, I'm going to add heat. If I want to take liquid water and I want to vaporize it, I'm going to add heat. Okay, so kind of from left to right, we are going to add heat. Okay, or I could say heat is absorbed. Heat or energy absorbed. And on the next slide, we're going to say how much heat is absorbed. Now, if I'm going to go from a gas to a liquid, okay, if I'm going to go from a liquid to solid, you may not detect it, but actually heat or energy, same thing, is released. And it's going to be released to the environment. Okay? Heat is absorbed from environment. So all of those heats, whatever phase change you're doing, whatever heat you need to add or take away, those are all called latent heats or latent energies. Okay, latent heat phase changes. And we talked about that already, but we're going to talk about it again. So I like this slide. It goes ahead and gives quantities. I think I complained about chapter 2 when we talked about the same thing. It didn't give quantities. So for instance, I think it's 1 gram. I'm not sure. But see, with regard to melting, you have to zap it with 80 calories in order to get, I think, 1 gram to go from a solid to a liquid. Okay? Notice if we were going to go ahead and go from a liquid to a gas, we would have to zap it with 600 calories. Okay, now if we were going to go from a gas to a liquid, okay, notice that it would release 600 calories of energy. This right here, this condensation, I'm going to write clouds, okay? Though that is such an important sort of energy released. We're going to actually see that again in chapter 4. It's very important. Energy is released as water vapor goes to liquid water. And the same amount of energy that was required is also released as you take a liquid and solidify it. And then we talked about these up here, kind of the long arches. The pink arch is where actually it's going from a solid right to a gas. We call that sublimation. I think I used the example as dry ice. It goes from a solid to a gas. Example down, and then about 680 calories are required. It can go from a gas to a solid, and a good example of that is frost. Okay, and in that case, 680 calories are released. So.
Like fog. Fog, yeah. Settling over.
Yeah, as long as fog is a solid, yeah. Cool. So, last slide for now. So if frost is the whole vapor going to a solid, we call that deposition, and about 680 calories of energy are released. This actually isn't necessarily deposition, but probably fog is liquid water, so it's going from a vapor to liquid particles, so about 600 calories are released per gram.
You have to know those numbers.
No, you won't have to know those numbers. So let's take a real quick look at Chapter 3 assignment. Here it is. Is that Chapter 3? I guess so.
Yeah.
Okay, good. So number 2, this looks like it's under give it some thought, maybe. What am I thinking? So this is what it looks like, what you should be answering.
Actually, I switched my project.
Oh, goodness. So use this to say which one is Urbana, Illinois, which would be a continental location, versus which one is San Francisco. And we talked about the one in San Francisco should have the ocean kind of moderating it, okay? And you're supposed to go ahead and say how you figured that out. Number 3, just do your best. I have some students who say, yeah, I totally get that. Basically, we talked about the presence of clouds during the day have a cooling effect. If you have clouds there, your daytime temperature is going to be cool. And what's going to be at your nighttime temperatures if you have clouds? Warmer, exactly. So kind of with that in mind, kind of asking you some questions about combinations of clouds at night, clouds and daytime and nighttime. All right, the next one looks like this. This is the figure you're referring to. Remember, this was through the course of several days. We kind of have our daily maxes, okay, our daily mins, and you're supposed to use it to determine the maximum temperature for each day. And then go ahead and once you have the maximum and minimum, remember we said how can you get an average if you have a maximum and minimum?
Add them and subtract 2.
Add them together and divide by,
Divide 2.
yep, add them together and divide by 2, exactly. So that's what you're going to do for each of those.
I have a question.
Uh-huh.
On 5/19, so the minimum on that day would be on the left side,
519. Yeah, I'm thinking so.
Okay.
Yep,
Make sure I was reading that right.
yep. Okay, so for this one, this is what we tried to do today. Basically, you find temperature along up here at the top, okay, and then you find wind speed over here, and you see where they intersect to knock out a wind chill temperature. And then this one, remember mean means average. Oh, sorry. Well, you don't need to know that. This is actually, I think I have more hits. So, this is the last one. This is where you need to compare 55 to setting your thermometer at 65, and you get 10. And then you need to compare 40, setting your thermometer at 65, and you get 20. So basically, you add those two together, or you would start to add those two together to know how many heating degree days. For the first one, the heating degree days is 10. For the second one, the heating degree days is 20. Okay. And this one, I don't think you need to do complete sentences. And it says, this one just says, how would you compare using more fuel when it's colder? And I think you can use those numbers to your advantage. Yes. Okay, so that's it. I promise. Have a good weekend, everybody.